Hi, welcome back. In this lecture, I would like to talk about how to encode vectors with quantum states and quantum states amplitudes. It turns out that there are two ways to encode vector values in a quantum state. The first one is called state encoding. So we're going to use a different quantum register to represent our vector. And the second one is called amplitude encoding. So we will use the amplitude of our quantum states to encode the vector values. So let's start with the first way to encode our vector values in the quantum states. And the first technique is called state encoding. As an example, we want to encode the vector v with 4 components. The first value is 0, the second element is 1, the third element is 2, and the fourth element is 4. So state encoding is probably the most obvious approach to represent each of these elements of the vector. And for doing that, we're going to use for each element of the array a different quantum register. So we represent each component of the vector v in the state of a distinct QPU register. And this QPU register will use an appropriate binary encoding like we used before. So let's see an example here. For the first element, that is 0, we're going to have our QPU register 1, and then we encode 0. For the second element, that is, the value is 1, we're going to use a second register, and then we're going to encode 1 here. The third element, we have an additional quantum register, quantum QPU register 3, and then we encode state 2. And finally, we have the fourth element, and we're going to use a fourth QPU register and encode the value 3. In this state encoding, obviously the number of a quantum register is also equal to the number of vector elements. So the more elements that we have, the more quantum registers we're going to have it. So what is the first problem? Well, the problem, as we saw in the previous slides, is that this approach is quite heavy on the qubits and the number of quantum register that we are going to use. The major disadvantage is really the amount of quantum register that we need to have to store a vector. However, also we have a few benefits. So when using state encoding, we do not need the QRAM. We can simply store the vector components in the standard RAM and use the individual values to dictate how we prepare each separate QPU register. To address this limitation, a second encoding called the amplitude encoding has been introduced. In this case, differently from the state encoding, we use one single QPU register, and we store the values of the array as the amplitude of different quantum states. So suppose we store the components of a vector in the superposition amplitudes of a single QPU register. So in this case, we just use one single QPU register. Since a QPU register of n qubits can exist in a superposition of 2 to the n amplitudes, meaning that we're going to have 2 to the n circle to play in our circle notation. So we can imagine encoding a vector with the n components in a QPU register of log n qubits. So this is a major saving. So instead of using different quantum register, we use just one quantum register with enough qubits to represent all the number of elements we have in our vector. And then we use the amplitude to represent the values of our vector. So in this case, the first element is 0, so the amplitude is 0, and then is 1, 2, so this is corresponding to this one, and then this one, and then this one. As you can see, is increasing because we have 1, 2, and 3. So these slides compare amplitude encoding on the left here to the state encoding. As you can see here, with the amplitude encoding, we have a huge saving in terms of the qubits that are needed. So here we just need 2 qubits. Here we need 2 qubits multiplied by 4. So that's a huge saving when we use amplitude and encoding instead of state encoding. And here another example, for instance 6, 1, 1, and 4. So you see this is correspond to 6, 1, 1, and then 4. And so we encode it in the amplitude of this circle. And again, is a major saving when it comes to the number of qubits we need in our system. So far we saw all the beautiful things about amplitude encoding, so allow us to use a reduced number of qubits. But what are its limitations? Well, one limitation is the quantum superposition. So we have the amplitude and we have the superposition are generally unreadable. So if we spread the components of a vector across a quantum superposition, we can read them out again. So we will just read one value, not the full amplitude of the quantum state. However, through the process of measurement, we can still often extract useful information from an amplitude encoded output. For instance, if we repeat the measurement many times, we can calculate the distribution. So an example here, for instance, we encode this vector in the amplitude. Encoding we read, is very likely that when we read, we are going to get state number 3, right? Because this is the most likely to count. So what is the second issue? Well, you probably realize already at this point is that the values that we can encode within this amplitude encoding must be normalized, right? Because these are quantum state, so this is amplitude of a quantum state, so these must be normalized. So the question is, can the amplitude of a 2-qubit register really take the values of 0, 1, 2, 3, or 6, 1, 1, 4? Well, the answer is no, because this value must be normalized. So we know that the law of quantum computing, the squares of register amplitude must sum to unity. The reason is that this represents a probability. And because these are probability, we need to have normalized values. So what is the impact of this normalization? So for instance, we have this example vector 0, 1, 2, and 3. We need to normalize, so we need to divide by the norm of this, that is 3.74. And this, when divide this vector by this, we get this normalized vector here that is not exactly this one, right? So we see these two vectors are different. This is the normalized. However, using this vector here that is normalized, we can now encode it in the amplitudes of superposition. So does the normalizing vector have any adverse effects? Actually, normalization leaves most of the important information intact. That is the global structure. So what it does is basically taking our vector and basically rescaling to be 1 as a norm. So as you can see, all the global information, that is the direction of the vector, is intact, and what is going to change is the actual amplitude. So geometrically, normalization rescales the length of a vector while leaving its direction unchanged. So the global properties is kept unchanged. This is the last slide of this lecture, and talk to you soon.